So last time we were discussing binomial heaps. So these are binomial heaps. 1 second. By the way, can you hear me and see my screen? There were some network issues because of which I got delayed. Yeah. So so we saw how to. So these binomial heaps are structures in which you can construct the heap, find the minimum element in the heap, insert a new element in the heap, delete the minimum element, and combine two heaps, an operation called meld. Correct? And we discussed last time ways to do this, which in which this make heap, find min, insert are all order 1 time operations, and meld is order log n time, and delete min is order log n time. Today we are going to first see how to do meld in order 1 amortized time also. Okay, and we are going to explain it. I'm going to explain it in detail. So do you want me, are there any questions about last time? Hello? So last time everything was clear, was it?
Sir, the meld of two general trees are also logged.
The meld of two generic trees, meaning
No,
two
heaps.
two binomial heaps.
Yeah.
Yeah.
So what's the time complexity of that?
So the algorithm that I told you about takes order log n time.
Wherein there's a total number of vertices in both the trees?
Yes, where n is the combined count of the vertices.
Okay, sir.
Correct. So and why is that? That's just because we do this binary addition kind of thing, and there are log n digits roughly, and summing them up takes log n time. Correct. So order log n time. Correct. Now today we are going to see how to do. So we are going to see a lazy version of meld. So lazy version of meld and of insert. So insert also took the same time as meld because insert was actually implemented in terms of meld. Correct. So so how do we do that? So notice that when we compute the meld of two heaps, in some of the times the carry will propagate all the way through. We'll have to so for example, when you do an insert, a single insert, correct, the carry would take time log n only if the other heap was contained trees from of all sizes, of all classes, of all ranks. Sorry, so I was calling it rank. So of all ranks. So if you had something like 1 1 1 1 for all login bits were 1, and then you added 1, then you would get 1 0 0 0, and this would take login time. But in many cases you will see that if, for example, if you were to add 1 1 something 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 0 and you add 1, then this would take just order 1 time. Correct. So how do we make this precise, this notion that on an average it will take order 1 time? And the solution that we are going to see is based on an idea called amortization. So So how do we do it? Well, uh, the idea is that when you insert an element, so we will maintain some savings accounts for each tree, correct? So we will maintain every tree has 1 rupee in credit available, correct? So what do I mean by 1 rupee in available? This means that when it is created, we think of it as spending one extra unit of time and storing it and attaching it to the tree, correct? So when you do an insert, are you with me?
Yes, sir.
Repeat the last point.
So so what I'm saying is, when you do an insert, you give the tree an extra 1 rupee. When you do an insert, you credit 1 rupee to the account of a tree, of the tree form. It's as if you are doing one extra bit of work, which you are giving it one extra time, this thing which will be spent later whenever needed, correct? Now, similarly, when you so in all these operations, in all the order one time operations, you give you spend one extra, you provide one extra bit of time. So here in make heap doesn't, okay, make heap, yeah. So make heap, when it creates a single element, this thing, you give it 1 unit of time. In find min doesn't require that because it doesn't change anything. Insert and okay, in these two you give 1 unit of time, one credit to the tree in which you are insert, correct? And now delete min gives order login, and with these extra credits you can do meld in order one time. So let's see how. So um, so uh, basically when you take the sum of, when you link one tree to another, so what is the time spent on when you are doing this melding? It is spent on linking, correct? Are you with me? So you have this b login, b login minus 1, and so, or let's not call it login, let's call it, give it some name, uh, bm minus 1, bm minus 2 till b0, and there is another such bm prime, bm minus 1 prime, and b0 prime, correct? So now when you do the melding, you will combine b naught and b naught prime. If there is a tree there, if there is a 1 here and a 1 here, you'll spend time to link one of the trees to the other. So then you utilize the credit that this tree had. So you will link one of the trees to the other tree, the tree with the higher value to the tree with the lower value. The lower value thing remains on top, correct? So then you spend the one credit that the higher value tree had in doing this operation. Okay. And similarly, when you add bi to bi prime, you have one credit with each one of them, and the one that is linked spends its credit, uses its credit to pay for the operation, correct? So Are you with me? Am I making sense?
Yes, sir.
And in delete min, why do we spend login time? Because in delete min, what happens? You have some BI that is connected to several trees, correct? And you cut these trees, correct? So you remove these trees, make a new heap out of them, and so these trees are exposed, and they don't have any credit, because the credit is only for the root of the tree, for the entire tree itself, correct? So you have to give them 1 unit of credit each, which the delete min, of course, can do from, because it's anyway spending order login time, it can spend one more login time. Am I clear? Somebody who has not seen this before, if it's not clear, tell me. So let me write this down. When you link two trees, the tree with the larger value pays for the operation by its credit, correct? And we just maintain that every tree has 1 unit of credit. Correct? So this is just for insert. And meld is so meld is very similar. I mean, in insert is a special case of meld. You maintain instead of, so so remember, the trees are strung on a doubly linked list. We said that, correct? So the heap contains a doubly linked list linking all the trees, the roots of all the trees in the heap, correct? The are you with me? Sorry, I'm not getting a sense of whether I'm getting through or not.
Yes, sir.
Okay. Others, somebody else? So the trees, the roots of trees in a heap are kept in a doubly linked list. And now you follow the pointers in the list and create. So whichever ones of these are non-empty are kept on the list, and whichever ones are empty are of course empty. And now you take the two lists from lower to upper, this thing, and from the lowermost point to the uppermost point, and keep on combining, linking things where there is a 1 or there is a carry from before, and so you have 2 1s or 3 1s, whichever way it is. You link two trees and pay for the linking operation by the credit that one of the tree had. So one of the tree gets linked, loses its credit, and now the tree is left with one credit only, and now you can do this. So please tell me whether this is clear. If this is not clear, other future things might not make sense.
Sir, the list is doubly linked so that like we can move forward and backward.
The list is doubly linked because we want to move forward and backward. Yes.
Okay, sir.
Why do we want to move backward is not immediate to me, but
Then like why do we need doubly linked list, sir?
that's a good point. That's a good point. Uh, that's a good point. I would have to think about it. Uh, so, but doubly linked lists don't cost much over the singly linked list, correct?
Yes, sir.
I mean, just a constant amount, so it's okay. Uh, now,
Sir,
tell me.
so far I kind of get what's going on, but at some point, could we work through an example with
Work out
the,
an example.
yeah, just go through an example of one of the operations with the amortized thing at some point. Maybe not now.
No, we can do it. So we saw an example last time. So suppose you have one heap containing B4, B3, B2, B1, and the other one containing this set, whatever is written, B4, B3, B2, and B0. Correct?
Yes, sir.
Now you now you want to meld the two things. Correct?
Yes, sir.
So you would proceed from the 0th this thing. You would spend order one time. So okay, that's a good point. That's a good point. So I did not explain some things. So you would, of course, in the linking part, so uh, so yeah. So 1 second. So so the linking part is paid by for the paid for by the linking tree, the tree that is linked, correct? But apart from that, you have to pay for these order log n many extra things because you're traversing the list. Even if you don't uh, link them, you would have to pay for them, correct? So, so how do we argue that? How do we argue that this order login thing is paid? So the idea is, suppose you have uh, m trees and do k links. Suppose you in a meld operation you have m trees and do k links, correct? So then you after doing the k links, you will end up with how many trees? M minus k, because each link decreases the number of trees by 1. Correct?
Yes, sir.
So, so now you have, so the total amount that you spend is M plus k, correct? And you have to somehow do an accounting which shows that this M plus k can be paid for by, correct?
Yes, sir.
So m plus k is basically m minus k plus 2k. This m minus k is the number of trees that are there at the end, correct?
Yes, sir.
And 2k is the number of links that you do, and so k is the number of links you do. They are paid for by the credit that the tree gets, correct? But now where does this m minus k come from? Notice that m minus k is the total number of trees, so this is less than log n, correct? So this log n was paid for by the delete min. Why is m minus k less than log n?
M was log n, right? So that should be less.
M is not m
Sorry.
is less than 2 log n, but
yeah. Sorry,
m minus k is less than log n, because finally all the trees are distinct, have distinct ranks, correct? There are m minus k trees, all of distinct ranks. I mean, these are the final ranks, and so therefore they are less. M minus k is less than log n, and now this log n so this log n will be paid for by the delete min, that is before. Okay, sorry, I made a botch of things. I botched up things badly. So let me do it again. So if we do it so I mixed up eager heaps and lazy heaps. In lazy heaps, we do not so in eager heaps we do maintain this we maintain the minimum pointers and everything, and sorry, let me start again. Let me start from a while ago. So so eager heaps, you see, take a log n time, correct? Now we want to decrease this time. So instead of doing it in at every step, instead of so instead of doing this linking and everything, so doing this summation thing, this binary summation at every step, what we do is we do not do it until we need to do it exactly. So when do we need to actually so basically in lazy heaps we just concatenate the lists that we get. So suppose you want to meld two trees, you just concatenate the two lists, correct? Without regards to whether there are distinct, there are all the ranks are distinct or not. You just combine the thing, correct? Are you with me? So
yes, sir.
So for example, in this case, H1 and H2, you would just take the union of the two lists, correct? And this you can do in order one time, correct? So when delete min comes, then you fix the heap, so to say. So how do you fix the heap? You go through the heap and the linked lists, and you so basically you so in this thing you would have two B4s, two B3s, two B2s, one B1 and B0, correct? So you would form a new list in which you would start adding B0, and then if you see another B0, you don't see another B0, so that's fine. Then you see, let's say B1, you, or whatever you see, in whichever order you see, you add it to the corresponding, no, one second. One second. Now I'm getting confused. So some of the idea, let me explain the idea to you, and then we can quibble over the details. You take the so the you take the two B0s and you spend some time over it, and then you, or there's just one B0, so you spend one time over it, and then you go to B1 and you spend one, in this case only one time over it, and then here you need to link, and you pay for this linking by the extra credit that this B2 had, that the tree had, correct? So one second. So let me do it. Let's do an example, like someone suggested. So you have this B4, B3, B2, B1, B0, B4, B3, B2, B1, B0, and this was H1 and H2, and this was 1, 1, 1, 1, 0, and this was 1, 1, 1, 0, 1. Correct? So you have a linked list, doubly linked list, in which you have this B4, the first B4, the B3, the B2, B1, B0. No, sorry. So there is no B0, correct? And then again, there is a B4, then there is a B3, then there's a B2, then there is a B0, correct? So now you create a new list with these B5 till B0, and you start putting things in the appropriate slot. So you create you string in, so, or rather you just string in the, let me just put, so you take this B4 and put it here, correct? Then you add B3, then you add B2, and then B1, and then you come back to B4 and you add 1, and you so this would give so B4 plus B4, you would link them, and this would give a B5, and this would just point here, and now you go to B3, and B3 would contain would give a B4, which you would put, so this is gone, you would put this is gone, you would put B4, and the order does not matter, correct? Do you agree?
Yes, sir.
And then B2 and B2, and you would put B3 here, sorry, B3 here, and this B2 would go away, these two B2s would go away, you would be left with B1, and then you attach B0. Correct? So basically, you are just summing up the things of with powers of 2. And k links occurred, like I said earlier. Now you know that after k links, after linking, after all linkings, m minus k trees survive. Correct? Because each linking decreases the number of trees by 1. Correct? So and all these m minus k trees have distinct ranks. Correct? Correct? So m minus k is less than equal to order log n, less than log n, in fact. Correct? And there are also these k links. Okay, so and 2k is paid for. So this is paid for by the delete min.
So what is this method of linking called?
Huh?
What is this method called? The specific one?
It's just a linking of two these things. Huh? So you have a tree, a bi minus 1, and you attach this bi minus 1 to the root of it, making it into a bi.
No,
So
I understood that. I'm asking what is the name of the thing you were doing?
I don't know of any name.
Mentioned two different names. They differ by the time complexity it takes.
Oh, the lazy this thing.
Okay, yeah, that's what I was
No,
asking.
that linking was not. No, the lazy applies to this lazy meld. So you link in both the cases, but in meld you do it lazily. You do not do it until it is required, and when it is required, it's paid for by the delete min that that is required, that you do. Correct?
Yeah.
So so basically, why do we do it while doing delete min is because at that point we need to change the structure of the tree, and we need the minimum. We need to extract the minimum element. So you might as well clean up the tree. Correct? So in this process, you also find the minimum element, remove it, meld the remaining things, and clean up the tree. Correct? Till that time, if you required min, you could just so while melding, you could store the minimum of the two elements and keep the min pointer, update the min pointer only, but not do the cleanup. Am I making sense?
Yes, sir.
Okay. So now what we are going to do is another data structure in which we
Sir,
add. Tell me.
could you explain this m minus k and 2k paying
Huh.
things?
Huh. So what I'm saying is, if you have m trees and do k links in a delete min, so what is the time you will spend in this delete min?
K links would take.
No, overall time. You would have to traverse all the m trees and you would have to do k links. So total time taken is m plus k. Correct?
Yeah.
Now you want to say that this m plus k is paid for. So the k links are paid for by the credit that the trees have, correct?
Yeah.
But the operation on these m things is not clear how we will pay for those, correct?
Yeah.
So we write our m plus k, the total time, as m minus k plus 2k, correct? So you can charge this 2k to the linking step, correct? 1 credit, 2 credit, whatever. Suppose you are given 2 credit instead of 1 credit always, correct? So you charge this to the linking step, to the credit
But
that you have.
we only have k links, no? Like, so that should only contribute to k.
So what I'm saying is this m minus k is a log n plus 2k. This is equal to order log n plus k. So think of this k as being the credit for the uh, from the trees, and this log n coming from the delete min. Am I making sense? So
I'm
you
still not clear about it. Like, each linking only contributes to like 1 rupee. So how can you do it for 2k?
so let's say you give, instead of 1 credit, you give 2 credits. Then it's fine, correct?
Oh,
Correct?
yeah, and then m minus k would be just traversing the list.
So no, m minus k is the length of the final list. After k links, after k linkages, m minus k elements should be left, correct?
Yeah.
So that must be bounded by log n, because these are all the trees have distinct ranks.
Okay.
Correct?
So this is order log n plus k.
So this is order log n plus k. Log n you can charge to delete min. And this k, order k, comes from the credit that this thing had, correct?
Okay, so yeah.
Okay. So now we do something slightly more complicated. We add the two functions decrement. So this thing is hi delta, which means that decrease the value of item I by delta, correct? In heap H. Okay. And the second operation we will do is delete H comma I. Okay. Okay, are you with me?
Yes, sir.
Okay. So how, let's do delete first. So when you delete an element, you just instead of delete min, you just take that element and you just remove the so it is somewhere in the heap. So I is sitting somewhere in the heap, somewhere below. You remove its children, all the subtrees below it, and just meld, form a new heap and meld it with the original one. Correct? So seemingly this is very simple, correct? But now notice that if you do this many times, then Then because you are taking things out from the middle of a tree, the tree will not remain, will not have, will not be a very, will not have exponential in the number of rank many nodes, correct? So previously we were just removing a minimum element, correct? Correct? So if you remove the minimum element from a tree, so if it is bi, you have b naught till bi minus 1 here, you remove the minimum element. Suppose this is the minimum element, you remove the minimum element, then you will be left with trees which are very dense. I mean, where the ith tree has, where this jth, this thing has size at least 2 to the j, correct? So this jth one has size at least 2 to the j, has size exactly 2 to the j, so you are fine, correct? But now if you have a large tree and somewhere in the middle you remove some part, then it no longer remains, so you might remove many such things, and slowly this tree no longer remains dense, it becomes very, I mean, it will not contain exponential in the rank many things, correct? So that is a basic problem that we face. Now, how do we do that? In order to do that, we will ensure that we never cut an element from a tree many times. We will only allow it to allow us, we will only be allowed to cut the tree twice at 2 points, correct? So,
Sir?
Tell me.
Sir, I might be misremembering something, but so suppose we cut something from the middle of a tree, won't it, it might stop being a binomial tree, right? So
yes, it will stop being a binomial tree.
So even if we meld the vertices back, somehow it will not be a binomial tree, right? So don't we want everything to stay binomial trees? Or,
no, so now we are now we are not constraining it to be a binomial tree. It will be something closely related if we allow just 2 cuts, and that we will call a Fibonacci. So these are Fibonacci trees and Fibonacci heaps, correct? So now we are in the domain of Fibonacci heaps, correct?
Okay, sir. Okay.
So so the point is that when you cut the first tree, correct? First, so basically, we will allow. So you have a node, correct? We will allow you to cut only 2 children from the tree, correct? So if in a binomial heap there are these this bi has I children, correct? That is, the rank is I and it has I children, and you're not allowed to cut anything from the middle. Now we will, with the relaxed this thing, we will allow you to cut at most 2 things from 2 children from this, correct? Correct? So in fact, we will not. So when the second child is cut, what happens? We will. So suppose these are B1 till these are trees T1 till Ti, and you cut one tree, correct? Some Tj you cut, correct? Now the second time you this so you cut Tj and then you start cutting Tj prime, correct? So when you cut Tj prime, you would just remove the root of the tree itself and melt the entire thing. Are you with me?
Sir, can you repeat it? The last point.
Okay. So what I'm saying is, so you have this T1 till Ti. This is a rank I tree, correct? And now you make it a rank I minus 1 tree by removing one of its elements, one of its children, correct? Say Tj is removed, correct? So this becomes a rank I minus 1 tree. Now if I remove another Tj prime, then I will not be allowed to remove this Tj prime. What I will do is I would remove this entire we would remove this root itself and meld it with the original one. No, sorry. So let me do it again. Sorry, it was not entirely correct. So suppose you have a tree T naught. So tree T, which has children T1 till Ti, correct? And this is the child of some T prime, correct? This is somewhere in the middle of the tree. You have a tree which has many children, and so now you cut this Tj, correct? You cut this Tj out, and you would take all its children and meld it with the original thing in a lazy way, correct? But now, if I try to remove this Tj prime also, correct? If I try to remove Tj prime, then I will instead do a cascading cut. I would remove this part, correct? And add this entire thing to sorry, what is I'm getting confused. No, so what is confusing me is this. So what we are supposed to do is this, that when the second child of a tree T is cut, we remove this uh, entire thing and meld it with the but still this would have two children missing. So this I don't understand. How do you Uh, do people see the problem?
Sir, are you saying that T dash will have two children missing?
T dash will have one child missing.
But do we remove Tj dash?
So suppose first we remove Tj, we delete the Tjth element, correct? So T has one element missing. Then we want to remove Tj dash. Then what will we do? So then we would remove, I think, yeah. So, yeah. So I think what would be done is that you take out this part, T, and this T1, Tj dash, Tj, Tj, and Ti, correct? Remove these two parts, and now you cut even this, and this becomes a new B naught. You add all of this to the thing, correct? No, that is what is confusing me.
Sir, is the problem that, sir, so we want every child to be something, to be a binomial array with at most one thing missing. Is that right?
Yes, yes, yes.
Sir, then what if we try to remove xj dash after having removed xj, or tj dash after removing tj?
Yes.
Instead of removing that, we just move t entirely. And if t dash is now missing two children, remove t dash entirely and so on. Is there a problem with that? Or
no. Yeah. So the problem is, T has suppose 5 children. Suppose its rank was 5 initially. After removing Tj, its rank became 4.
Yes, sir.
Correct. Now, if we so now you are saying in T dash's rank is more, we remove it from, so we reduce its rank by 1. So, correct. But what do we do about this T?
So is there a problem if we meld all the vertices in T with whatever tree is remaining?
So T alone we cannot. We have to cut down T also, correct? Because T has 2 gashes.
Oh yes, sir. T with all of its remaining children. So Tj has gone somewhere into the tree, and then now we have T and its remaining I minus 1 children, and we just meld that with whatever is left of the tree.
Huh. So you are saying we would remove. So does T become a zero rank tree or not? One option could be you take T, T1 till Ti, omitting Tj dash and Tj and so on, correct? No, am I making sense or no?
I don't fully follow, sir.
Okay, let me not confuse you further at this point. Let's defer the discussion till next time, correct? We'll quickly finish the discussion next time. I'm getting confused by some minor thing, and yeah, so let's do it next time, correct?
Okay, sir.
Okay, sorry about this today. Let's meet on next Tuesday. Next Thursday there is no class, correct? There's no lecture. Yeah, thanks. Bye.
Thank you, sir.
Thank you, sir.